for specific brainstorming problems to some extent. The next 3 sessions this morning, this afternoon there's some breakout sessions. We'll hear more about that later. But one of the recurring themes throughout this week, as David Newbury was suggesting just now, is that while there are a lot of traditional scientific challenges in the energy research, some of the real problems are in policy and in how economics affects policy. And something that a theme that's been beginning to bubble to the surface during the week is the fact that traditional economics is to some extent distorted by the large amounts of uncertainty involved in ongoing energy provision. So our next speaker is Dr. Nafis May, who is from the Department of Energy and Climate Change, and he's going to be talking precisely about that, about energy policy and how it interacts with the science.
Well, good morning, ladies and gentlemen. My name is Nafis Mir. I head the science team in the Department of Energy and Climate Change. I just want to say a few words following on from what Samantha has spoken about, because it's of critical interest to us that we engage with academics and through the research councils and bring in that learning that you are involved with into the department and into policy making. So a lot of what you do and what you're doing is absolutely essential for the development of the energy system going forward. So I was really pleased to listen to what Samantha was saying. Now, what I want to talk about today is the role of uncertainty in climate policy and the way uncertainty plays out in policy making, because uncertainty, by which I mean not only value uncertainty but also the deep structural uncertainties in the climate system, have an absolute profound effect on the way we frame the issue and the way we try to address the challenge of climate change. Now, I guess most of you will know about Donald Rumsfeld's famous encapsulation of the issue in terms of known knowns, known unknowns, and unknown unknowns. Well, climate change and climate policy is a perfect encapsulation of all those three categories. Now, the purpose of my talk really is to invite ideas, because I think we've got to the position now where there's quite a lot of information. There's an appreciation now of the deep structural, as I say, deep structural uncertainty in the system, and we are now struggling to see how we can use all the information we have, identify what the gaps in knowledge are, and even if we do plug those gaps, there will still remain uncertainties. So how do we move forward in terms of actual decisions? What are the optimal routes forward? So that's what I'd like. That's what I'd like to do. As a public policy issue, climate change is a classic example of what political scientists call a hard problem. Notwithstanding the compelling scientific evidence, it is contested. It's very highly contested, as most of you will know from the recent media coverage of the email hacking incident in the climatic research unit in University East Anglia, and following that, the concerns about the alleged mistakes in the IPCC reports, particularly the Working Group 2 report. However, we've got to recognise that there is and always will be irreducible scientific uncertainty. After all, we can't do a controlled experiment on the planet. But even if there is a consensus on the science, What it doesn't do is tell us what we ought to do. From the perspective of the decision maker, what are the trade-offs that the decision maker has to consider? That is something that facts, as they stand, do not tell you. So what I'd like to do is, over the course of the next 20 minutes, 30 minutes or so, is give you a quick run through of the science of climate change, what we understand now. Secondly, the 2-degree target, which has been agreed at the Copenhagen Accord, and we've been doing some analysis, commissioned some analysis through our Avoid program, and just give you a flavour of the messages that are coming out of that program. Then I want to move on to the key questions in the economics of climate change, because at the end of the day, what we need to consider as policymakers is how much this will cost, what are the trade-offs, and what we need to do. Now, many of you will know about Lord Stern's review of the economics of climate change, which was published in 2007. That has had a transformative influence of on the whole debate, and has also generated a great deal of vitriol in the academic economics community. So you have the sight of various Nobel Prize winners in economics bashing each other over the head with the various disagreements over parameters that are used and interpreted in Lord Stern's review. I'm going to touch on some bottom-up technical models, but just briefly touch on those because they give a slightly different perspective. And finally, I want to end with where does it leave the decision maker in the light of the developments in both the science and in the economics. So, starting at the beginning, carbon dioxide concentrations have been rising from pre-industrial levels of about 280 ppm, parts per million, and they're around about 380 parts per million now. Now you can see from that curve that the rate of increase is huge, and it all started in 1769, which, as many will know, is when James Watt invented the steam engine. So you can locate it as tightly as that. So, and this is from David Mackay's book, Sustainable Energy, who's a professor here. And we know we've got evidence that the CO2 is man-made. We've got data here from the Mauna Loa site in Hawaii, which has been monitoring CO2 concentrations over the last 3 decades. The bottom chart here shows the global carbon emissions of the last 30 years, and the chart below shows the ratio of the decrease in the C13 concentration. The isotope ratios give you an indication of where the carbon's coming from, and it's coming from organic sources. Since records began, since this monitoring has been started, actual measurements have been made since the 1850s. This is a chart produced by the Met Office of the average global temperature since about 1850, and you can see from this chart that the last 10 years have been the warmest decade since the records began, and there is a clear trend upwards. And from the global climate models, these are results taken from the Hadley Centre global climate model, the atmosphere ocean global climate model. And what this simulation does is show you the comparison between the simulated average temperature of since about 1850 with the actual measured temperatures. Now the measured temperatures are given by this black line here, and the green band here is the simulation without man-made CO2. Wrong one. With excluding human influence, with excluding man-made CO2 going into the atmosphere. And if you do include that, then you get a pretty good correlation with the actual temperature record. Now, the inference you draw from this is that we think the models are a good representation of the climate, and that the reason why we're seeing this increasing global warming is because of human influence. So, the IPCC in its 2007 report published this chart, and what it shows is the projected temperature rise over the next 100 years for different scenarios, essentially. These called the SRED scenarios. So these labels at the bottom give you different scenarios. So some are scenarios which assume, for example, a high population growth like A2, others that presume that there's going to be a little bit of, well, a high degree of renewables than others. Some are very dominated by fossil fuels, for example. So using these scenarios and the number of models, and there are about 14 models worldwide, you get an indication of what the temperature rise is likely to be over the next 100 years or so. And what we have is a conclusion that the scale of warming depends on the emissions. There's the low scenarios where there's quite a lot of renewables. You get a range of about 1.1 to 2.9, where we think this is the A1B, 1.8 to 4 degrees, and a high scenario where there's a high use of fossil fuels, 2.4 to 6.4 range. Now the ranges are quite large, you'll notice. We can live with 1.1 increase, but certainly would not be able to live with 6.4 degree increase in global average temperature. Now the models have looked at the spatial distribution of temperatures. They can look at spatial over the globe, and what you see from this is that the polar regions are warm much more than the equatorial regions, and also that the land areas warm much more than the sea. And indeed, when we look at some of the results from things like melting ice caps, we see that the temperature change in the poles is much higher than it is elsewhere. And comparing the sea surface temperature records with the land surface temperature records, you do see a big difference between land temperatures and sea temperatures. So as a result of this evidence, the IPCC in its fourth assessment report concluded that warming of the climate system is unequivocal, and that's evident from the observations of increases in global average air and ocean temperatures, widespread melting of snow and ice, and rising global sea level. So this slide just gives you the temperature trend and also the average increase in average sea level over the last 100 years or so. So the Earth's average surface temperature has warmed by 0.57 degrees since 1900. Sea level has gone up by 20 centimeters. The glacier, snow cover and sea ice are all declining. We are getting more frequent heat waves, droughts and extreme rain events. So, and indeed, there's a lot of criticism. There has been a lot of criticism, particularly in the press, from some quarters, that the IPCC exaggerated the extent of the changes as a result of global warming. In fact, more recent analyses have shown is that the IPCC have been conservative in terms of the changes that are happening. And what this is from NCAR, the National Centre for Atmospheric Research, and what it shows is a number of models runs of from different groups of Arctic summer sea ice extent, and that's the average in the black line, and you see the actual measurements are well below. It's thinning as well as decreasing in extent. So, impacts of climate change. At the end of the day, it's interesting to talk about and study the global increase in temperature, but what we're really interested in is what are the impacts of climate change with increasing global temperature. So the IPCC in its Working Group 2 report looked at a number of dimensions: food, water, ecosystems, extreme weather events, and risk of abrupt major reversible changes, and provided some work that indicated what might happen over these increasing temperature ranges. So at 2 degrees you start getting falling crop yields, particularly in the equatorial regions. By 4 degrees you certainly will get falling yields in many developed regions. There might be some positive effects because of CO2 fertilization effect in developed regions, about 1.5 degrees, but that goes the other way at higher temperatures. With water, we've got a significant problem with disappearing mountain glaciers, notwithstanding what the IPCC report said about 2035 the Himalayan glaciers will disappear. That was unfortunate, but nonetheless there is plenty of evidence now, certainly in the Andes, that the glaciers are retreating quite significantly. Significant decreases in water availability in many Mediterranean and Southern African countries, and sea level rise. With ecosystems, we are already seeing damage to coral reefs and a risk of extinction of a number of species. Extreme weather events, there is clearly an increase in intensity of storms and in heat waves. The 2003 heat wave in Europe caused an excess death of 35,000. Last year, DEFRA published the UK climate projections, which predicted that heat waves like that will be events that happen every 2-3 years by the 2040s. And risk of abrupt major irreversible changes, dangerous feedbacks, abrupt large-scale shifts in the climate systems. I'll say something more about that in a moment. However, we do have, and we have to acknowledge, the cascade of uncertainty in the climate system. So as we go from my right to your left, emission scenarios, there's a lot of uncertainty around that. I mean, when you think about it, reflect on it for any moment, there are huge uncertainties for example, in greenhouse gas emissions from land use change. Atmospheric concentrations, particularly of some of the greenhouse gases, methane, nitrous oxide, for example. CO2 is relatively well constrained, and we've got some pretty good measurements on that. Climate sensitivity, and I'll be speaking more about this parameter, absolutely crucial parameter. Climate change, what the temperature, precipitation, quite a lot of uncertainty about that, and the range of impact, even more uncertainty on impact. So as you go from the physical to the social, certainly you're getting increase uncertainty. And the other point to note is that the impacts will not increase linearly with warming. There are some things which will be sensitive to temperature and could flip over. There's work by Lenton a couple of years ago identified a number of these possible tipping points: dieback of Amazonian rainforest, shifting of the West African monsoon, the Indian monsoon. What's not mentioned here is the kind of methane release from permafrost and the clathrates under the ocean. So there is a potential at high temperatures, higher temperatures, that you get massive release and impact on the carbon system and the carbon cycle, carbon sinks in particular. But what we don't know is when this is going to happen and what temperature will trigger these events. I said I'd say something about climate sensitivity, and climate sensitivity is something that climatologists have been working on since the very early days. Now, it's essentially a thought experiment. What happens if you double the CO2 concentration from pre-industrial levels? So how would the climate respond? Now, you can do it in two ways. One is look at the historical record of temperature changes and correlate that with CO2 concentrations, and the other is through constraining it by climate models. Now, what you're doing there is looking at the energy balance in the troposphere and looking at the forcing at that level as you double the CO2 concentration. What we see is that there's a fat tail. So, although the AR4 estimated that climate sensitive was around 3 degrees, so if you go from 280 ppm to 560, the temperature change, the modal temperature change will be about 3 degrees. There's a range of and they said it would be in the range, likely be in the range of 2 to 4.5 degrees. That's roughly, although it's not a normal distribution, roughly around 2 standard deviations. But there is this long tail. And one of the things that is becoming more and more apparent is that what are the implications of this long tail? Just considering the Earth as a black body, you'd expect that just with CO2, you'd expect, without any feedbacks at all, that there would be a temperature rise of 1.1 or 1.2 degrees, and that's a result that's been known for about 100 odd years. With feedbacks, and there are a number of feedbacks in the system, what they do is they essentially accelerate global warming. So the number of feedbacks there are, the major ones are here: water vapor, cloud. But the effect of clouds is very complicated, and one of the things that is not well understood at the moment is what clouds do. There's ocean circulation and ice albedo. Now, taken together, they increase that sensitivity, so you get instead that, as I say, 3 degrees temperature increase. Why there is a fat tail? Well, there's been work done by Rowan Baker. Essentially, it just falls out of the relationship between sensitivity and the feedback. If the feedback is a normal distribution and it's covered by this relationship, you would expect this fat tail. Now, this will become, I'll come back to this when I talk about the economics of the situation. But before I do that, I just want to give you some results from our avoid program. What the avoid program is doing is saying, okay, we've got a 2 degree target, which balances the risk against technical and social feasibility in an informal way, although this is highly contested. Can we predict can we project a model what the optimal trajectory should look like for emissions over the next 150 years? So we've kind of varied a number of parameters in this: the year of peak emissions, the emissions rate leading up to the BAU, the business as usual scenario, the emissions reduction rate following the peak, this here, 1 to 5%, and the long-term level of emissions. And that's essentially the floor of emissions below which you can't reduce. And what we find is, what the messages are, just to say that you avoid using a tuned, simple climate model called MAGIC, is that the global average temperature is determined by the cumulative emissions of greenhouse gases. So it's 2.6 teratons of CO2 equivalents over that period, 200 to 2,500. But the take-home message from this is that there are a number of trajectories that will meet the 2-degree target, but it's going to be a huge challenge. What we need to do is peak quickly, the next 5 years or so, 10 years at most, and thereafter there's got to be a very strong decline. Now, when we're talking about 5% year-on-year greenhouse gas emissions reductions, that means a complete transformation of the energy system throughout the world in a very short space of time. So, given that the science essentially provides an imperative that says that we have a real problem, the next question is, for policymakers, is okay, well, how much will it cost to stabilize the climate and avoid dangerous climate change? It's absolutely crucial, because it can't be the case that you stop doing everything else and use all your resources for one end. There are a huge number of problems around the world. So the second question is, will the cost of avoiding dangerous compete with other priorities such as development? And this is at the heart of some of the big debates in the economics literature. How do you value future benefits compared with current benefits? How do you value future generations with generations now? We might say that treating it as a simple net present value issue, then if we just apply the appropriate discount rate, we might say action would be justified on cost-benefit grounds if the present value of the benefits was greater than the present value of the costs. Or if there was a range of alternative policy actions, we can choose one with the highest net present value and say that policy action is the one that we should take. Unfortunately, it's as you'll have gathered, it's quite complicated. It's not as simple as that. It is a formidable challenge, because we do not and cannot know the precise benefits of policy action, given the underlying uncertainty. We do not and cannot know the future cost of the policy because of the very long time horizons. The cost and benefit functions are likely to be very highly non-linear, and we don't know what they are. And if the standard economic models are based on marginal changes, which they are, how do we account for big irreversibilities in the system once you've lost, say, something like the thermohaline circulation? What do you do? How do you cost that? And given the very long time horizons, what is the appropriate discount rate to use? Notwithstanding that, there's been quite a lot of work developing economic models of climate change. Now, to give you an idea of the complexity, they take things like technology, capital, population, estimate emissions, the atmospheric concentrations of gases, the forcing, the regional climate weather, and then environmental impacts and socio-economic impacts. So you can imagine, taking over the globe, it's going to be a very highly aggregated system, which they are. And these models, these integrated, there are different other models, but I'll focus on integrated assessment models for the purpose of this talk, seek to integrate the science and the economic theory to optimize climate policy. And what these use, they use the standard kind of social welfare economics function of maximizing social welfare, which is a function of the pure rate of time preference, that's the discount rate, consumption at time, and the utility function. And this is fairly generic for most of the most of the integrated assessment models with some slight differences. What do they do? Well, what we get in terms of outputs are a reference case, a BAU without impacts, a case with impacts, and the policy. And this is against global economic activity over time, so be about 100 years, 2100 there. So there's your cost of the policy, and there's your benefits of the policy. So that's the kind of general approach that's been taken. In the Stern review, I should say with the Stern review, he says that the integrated assessment modelling is at pains to identify that, explain that IMs have severe limitation. Nonetheless, the main conclusion, the key finding, and the headline that came out of the Stern review was that the cost of trajectory consistent with a 550 ppm CO2 concentration, E concentration in the atmosphere, would cost around 1% of global GDP per year, but the avoided damages will be 11% of GDP for a baseline climate and 14% for a high climate. So in terms of cost benefit, clearly it was cost effective to do that. There is, in this model, which uses page 202, there is some account of risk and uncertainty through Monte Carlo simulations of the climate sensitivity parameter and assumptions on risk aversion and equity. Now, in contrast to this, other integrated assessment models suggest a higher level of cost and a lower level of damage. So these are examples of a few of those: DICE, MERGE, and FOND. And the other models instead propose what's known as a policy ramp, and that is modest rates of greenhouse gas reduction. Now, one of the things that struck me when I went to a conference last year was how blithely a lot of my economist colleagues were talking about 4 degrees and 5 degrees and the relatively small damages associated with that. And I thought there needs to be a reality check here. But nonetheless, this is what these models are putting forward as the optimal policy response. Now, there's been a huge amount of debate in the literature about the Stern review, and the main criticism has been around the choice of discount rate and the idea that it should have used the market rate of between 3 and 7%. The Ramsey formula on social discount rate, which is used in all of these models, delta here is the pure rate of time preference, which Stern sets at 0. Now, that is the ethical issue there, as I mentioned at the beginning, is about whether you value future generations more than you value current generations. The elasticity of marginal utility of consumption, which gives a measure of the view on income inequality. Stern sets it at 1, and finally the growth per capita consumption. Now, taking all these together, Stern comes with a discount rate of about 1.2%. Most of the other models use discount rate of about 3 to 7%. And of course, with a high discount rate, basically you end up saying, well, it isn't much worth doing anything. So a high discount rate here just falls off. So the present value of the future is much lower. Now, there is that. More recently, there's been an interesting think piece by Martin Weissman, who's at, I think, Yale, and he's been looking at the, in a sense, revisiting the science. He's an economist who's been revisiting the science, and he's been looking at the implications of the fat tail in climate sensitivity. And then what he's done is translated the PDF of the climate sensitivity into confidence level, quick calculation, as a kind of back of the envelope calculation, as a function of greenhouse gas concentrations. Now, if you look at this table, at 550, there is a 10% chance of temperature being greater than nearly 5 degrees. Now, his conclusion that this is disturbing and can't be ignored in formal economic modelling. The last time the temperature of the world was 5 degrees higher than it is now, there were dinosaurs at the North Pole. It is a completely different kind of world from the one we experience now. He also interestingly looked at the damage function and did a thought experiment on what if you change the damage function that's used in integrated assessment models, and a lot of them just take something simple like this, polynomial quadratic, where C star T is the welfare equivalent of consumption, which he defines as a fraction of consumption that would be at initial temperature. What he says, though, is that it's impossible a priori to know what the functional form should be for high temperatures. We've never experienced high temperatures. There's no evidence for this. And if we go to something like a quartic or a cubic or an exponential form, then the damages would be much more concave. So for a quartic function which you use at 10 degrees, essentially you get a catastrophic loss. Essentially, consumption goes almost to zero. So, what does that mean? Before I go on to that, I just want to mention some other approaches, and we use this McKinsey curve as an example. And these are bottom-up estimates based on marginal abatement curve. And just eyeballing this, you say, well, okay, actually, it's not going to cost too much. So a bottom-up technical approach to greenhouse gas reductions gives you an indication that for a relatively low price per ton of carbon, you can get up to about 40 gigatons of carbon abatement. That's the potential of carbon abatement. Now, of course, one of the problems here is all this apparently low-hanging fruit that's been proved to be anything but low-hanging. But generally, these bottom-up approaches are optimistic and seem to suggest that it can be done at a comparatively small cost. And similar to this kind of approach is Sokolov's wedges. So the technical perspective seems to indicate that this is doable, and it's doable at a relatively moderate cost. A lot of the formal economic analysis is suggesting the complete opposite. So where does that leave the decision maker? And what I want to do is leave you with some questions, because I think the policy community is struggling with this. To some extent, if you take what was said at Copenhagen, the agreement on 2-degree target, the agreement on getting massive international financial flows going, the 100 billion a year, it seems to suggest there's a recognition, a consensus amongst policymakers around the world that this is a problem that we have to do something about, and do something about this urgently. On the other hand, I'm willing to bet that over the next 2 years we're going to have a very detailed, fractious discussion between the various countries, various interests, and they'll point to the economic analysis which says, well, we don't have to do much now. We can wait and see. So given that, what are the choices facing decision makers? Well, one of the questions I would like to leave you with is formalised cost-benefit analysis for climate policy? And if the answer to that is no, what alternative should we adopt? If the 2-degree target has been adopted as the target, should economic analysis focus on seeking the most cost-effective pathway to do that? Or alternatively, should we move to a different framework based on risk management, formalising the precautionary principle. Now, I think the second, this penultimate point, I think it is clear. The answer to this clearly must be yes. Do we need more scientific knowledge on threshold temperatures for major continuities or catastrophes? I think we certainly need to do that. Question is how. And what else is there? Is there any other approach that we policymakers need to consider? Is there any other way of framing the issue such that it will enable decision makers to take the right decisions? So thank you for your attention, and I just want to leave you with this, which I thought was quite interesting. Thank you.
Thank you very much indeed. Can I point out we're going to have some breakout sessions later on, experimental this week, when we can brainstorm these issues in a sense. But for the moment, we do have 5 minutes. There may well be some questions or clarification or general issues, so it be appropriate to take 5 minutes of discussion now. Sean.
So, just to me, I just try not to get too emotional with this, but the idea of looking at mean utility and making conclusions is absurd. I mean, the variance, given what the statistics you talked about, and given the uncertainty that's been talked about this week, the variance might be infinite.
Yeah.
And so the mean is only off by 10%, but the probability of extinction is 5%. Looking at average values is this naive as just flipping a coin to this side. And I mean, how could they publish a report and not talk about? I mean, what do they say about risk aversion? I mean, about the variance of their utility?
No, not really. That's what's surprising.
Outrageous.
That's what's. I mean, there's quite a lot of discussion about uncertainty, to be fair,
Yes.
and there's quite a lot of investigation about uncertainty. But the actual models, most of those models are deterministic models. The page 202 tries to introduce some Monte Carlo analysis in looking at one parameter, the climate sensitivity parameter, but the rest of it is deterministic like the others. So one of the issues coming from the background where with more involvement on the global climate models, where there's it is essentially probabilistic, it's framed in that way, it's structured in that way, to come to the economic models which are determining policy, and find that the treatment of uncertainty is quite radically different. Has been an interesting experience.
There's something in one of your earlier slides about uncertainty, and one point I'd like to make is that these uncertainties are not necessarily additive. Some of them will be subtractive, so that if you have a bigger uncertainty on one mode of energy consumption, you will have a smaller on another one.
Yeah.
So that the total of them may not necessarily be deduced from the sum of them.
Yeah. That may be right. One of the things that we do need to understand a lot better is the propagation of uncertainties through this change, because at the moment there's very little work that goes on. I mean, I don't see much work on error propagation or uncertainty propagation anywhere in the literature. So that would be quite I think, really useful. Dave Frame at the Oxford Institute describes it as a Christmas tree. So as you go from one community, because as you go along the chain, you go from one science community to another, and what happens, the uncertainty is there, it kind of goes down again, and it goes up again, it goes down again, like that. So he describes it as a Christmas tree. But because it's cross-disciplinary, no one really has yet taken an overview and say, how does uncertainty propagate through the system?
Isn't maybe part of the problem that GDP is used as a proxy for whatever happens? So I mean, extinction is GDP 0, which doesn't. It's a rather small factor in the mean. semantically, right?
Yeah, that's-
But in a sense, if you would say that, extinction corresponds to cost infinity, that would actually give a rather different picture.
Well, this is what Martin Weisman does in his book, in his think piece, and it's been very influential. There's been a huge amount of responses in the back of it. It says, well, okay, it is basically costs go to infinity. So, but the problem then is, what does that mean for now? And various responses said, well, are you saying that we should spend infinite amount of money now to prevent this catastrophe? Well, that clearly can't be right either. So, I mean, what it says to me is maybe this. What it says to me, this cost-benefit framework is not appropriate. It might help you understand some of the issues, but as a kind of decision tool, it's not the right one.
As far as I know, no one suggested spending infinite money. Alex, we don't have it.
Yeah.
I do. Is anyone in deck talking about this as if we were fighting something on the scale of World War II? Like, this is something where we should really put the country into it. I do wonder why we didn't put an accountant in charge during World War II, and how things might have been if we had. And I look at the business case and say, even if the business case for saving humanity doesn't add up, we should probably do it anyway.
Good point.
Unless I've been watching daytime TV, in which case I'll look at it the other way around and say, if the business case does add up, we probably shouldn't save humanity.
I mean, clearly there's some absurdities that fall out if you take this particular approach. However, there must be, at the end of the day, some kind of cost benefit, and whether it's a formalised cost benefit like this, which I think clearly doesn't work, you need to be able to say. Now, one of the responses to Stern was, in his use of zero discount rate, is it privileges future generations who are going to be richer compared with the current generation. And I can't remember, it's another Nobel Prize economist essentially said, look, if you care so much about poor people in 100 years' time, why don't you care about poor people now? So it's inconsistent for you to say, we care really about poor people in developing countries 100 years' time, but we won't give any money to them now. So it's a complex issue, lots of dimensions, and one of the things that we need to do, find a frame, is how do you get all these kind of attributes into a kind of decision framework?
But what I suggest is we do look at a war scenario and say, if we wanted to get Britain to zero carbon within 15 to 20 years, how much would that cost? On the grounds that it wouldn't actually be infinite money, it's a smaller effort than World War II, so we know it has a finite cost and that it's physically possible. And let's look at the cost benefits of that extreme decarbonisation scenario.
Essentially, that's what we're doing. I mean, the Committee on Climate Change said you need to get hit 34% by 2020 decarbonisation and 80% by 2050. So government policy now is driven by those two targets.
And now I'm suggesting 90% by 2030, and let's cost it as an extreme outer, and see how it compares to the benefits from that.
Yeah.
But my conjecture is it's really about a transfer of wealth. I mean, Americans are very proud of all the money we made in World War II from all the big projects, and a lot of people became rich with new businesses, and that's a lot of people in this room are excited about being rich with all the new industries that have come up with green energy. And a lot of traditional companies are going to go out of business, and I think it's that transfer of business that's really slowing down the process, and the political issues are much bigger, I think, than the technological ones.
Any more brief questions? We are going to have an opportunity to explore these issues much further this afternoon. In particular, there are a lot of issues for politicians and statisticians. Anything quick that's relevant now? Okay, well, I think we should break now for a piece to schedule. But there will be this opportunity later on. Thank you so much. Thanks again very much.